Good morning, Stephanie, Elizabeth, Omar. How are you guys? Let's see. How's everybody doing this morning? Yes, good, bad. Elizabeth, you good? Alyssa, Monica, Miranda, Gerald, Andre, Michaela. I wonder if I'm even hearable. Can you guys hear me?
Hear you. Yeah, we can.
Excellent. Thank you, Edward.
Yeah, of
Yay.
course. Can you see the chat, by the way?
Oh, no. Let me get the chat.
Look at the chat. I think Omar really wants your attention.
Oh, gosh. Thank you. Morning. Who wants? I wonder why it doesn't give him a notification. Oh, where is it? Hello, Omar. How are you? LOL, whatever that means. I'm a chat box gonna go too. Oh, not so much me. Oops, not all caps. I'm not yelling. God. Okay, so here I'm gonna put the chat box for. Should I put it here, or should I put it down so it's private? I don't even. Oh, so excuse me. So let us get along with things, and I want to review something, which is that metal ions can be decent acids. Oh my God, no one ever told me that. Mn plus. Iron, well, iron 3 is a strong acid, iron 2 is not. Look at these numbers here next to the metal ion, and they give you a value. And if the value is less than 7, that means that it's an acid. That means that it will promote, I don't know, actually. I don't know if it's really 7, right? Because in the, well, it's got the same as a Ka, right? It's got this ion here, which is not a base, right? This is, okay. So it's the conjugate base of this acid, whatever. But it's not really acting as a base right now. And then you got H plus. So this process is M plus water makes MOH plus H plus, right? So this is making acid, making free H plus. And if the pKa is less than 7, that means it's a decent acid, right? Well, it means it's acidic, right? So anyhow, these guys can do that. So nickel is 10 to the minus 10th, right? So the product of these ions divided by that ion will be 10 to the minus 10. Oops. No, don't do that. So does that make sense to everybody? I mean, it was a revelation to me. Look, palladium is 1 pH 1. It's a humongous hydroxide scavenger. Gold, they didn't even have gold up there, right? I know it's a very good hydroxide scavenger. So, yeah, zirconium. Zirconium is the best acid. Exactly. Zirconium, zircon, from cubic zirconium fame, is ZrO4. And so it's an oxophile, like chromium, cobalt, zirconium. Oh, look, they have titanium, they have vanadate. Remember that, or I think that's vanadate, I'm not sure. Okay, so moving forward, we're going to skip the stupid HCl fountain. That would be fun someday, but can't do it. So, polyprotic acids and bases. Did we already do this? Did we do this?
No, we didn't. At least I don't remember
Okay.
this.
Okay, I'll make short work of it, hopefully. Thank you. So we got oxalic acid, for example, is this, it's, it's kind of a cool acid, I must say, because it's just one hydrogen molecule away from CO2, right? So this is a good redox agent, right? If you oxidize this guy, you can make CO2, but that's a different story. Sorry to evangelize about that here. So its Ka1 is 10 to the minus 2 here, right? So that means it's a fairly strong acid. And you know it's a strong acid because this group here, the COOH, which is next to the CO2 that just ionized, this part of the molecule is electron withdrawing. That will increase the acid strength of this ion, right? Because it'll pull that electron density out and it'll stabilize this big old anion, right? And so that will increase the acidity of this proton, right? The next proton to come off is literally, it's 4 orders of magnitude in acidity less acidic, right? So this goes from pKa of 2.5 to 5.5, or something like that, right? So anyhow, then there's others. There's phosphate, has the phosphate ion here this is actually acting as a base. So you got gotta not say my password out loud. So there's a phosphate plus water makes monohydrogen phosphate plus hydroxide. So this is KB1. KB, because it's acting as a base, making OH minus, right? And then you can take this, do it again, and do it again, do it 3 times, right? And it goes up by like 5 orders of magnitude each time. So this is actually a fairly common thing. If the acidic centers are close to each other, then there's a 5 order of magnitude increase in the pK value each time. Okay, so and then carbonic acid is a little bit weird because there's a couple of equilibria that precede the carbonate acidity piece. So you got CO2 that gets hydrated, basically goes into the water, and then the pressure divided by the CO2 concentration divided by the pressure is 0.03, right? Whatever that actually means, it's just a ratio, right? And then that ratio, that aquated carbonate or aquated CO2 makes carbonic acid, right? By reacting with water. And this pK is 0.002. It's approximately 0.002, right? And then, actually, this is not a pK. This is an equilibrium between hydrogen carbonate and CO2. Sorry, I misspoke there. And then the bicarbonate ion, the hydrogen carbonate or bicarbonate ion. Well, call this hydrogen carbonate. Call this guy bicarbonate. That ion here, this can be an acid, right? And it's looks like a very weak acid, right? But it's not really this weak because when you define it, you have to include all of this junk in the denominator the aqueous CO2 and the bicarbonate and the hydrogen carbonate ion here. And so it's kind of weird because if you go, you just only count the H2CO3, right? So you make a normal looking Ka here, then it's much, much different. And it's like a normal carboxylic acid. It's pKa of about 4, right? So, and then you can, here's some other carboxylics, like acetic acid is 5, formic acid is 4, cyanoacetic is 3 because it's got this electron withdrawing cyanide group here. So that brings it down an order of magnitude. Glycolic acid is also pretty strong. It's similar to formic, but more acidic than acetic acid because it's got the OH group there. So these are just some examples. And to put them in context, the Kas are all in the 4s and 3 to 5, 3 for the weird ones, and then mostly 4 and 5 for the more normal acetic carboxylates. Right? This diprotic, it's weird, right? But oxalic, which we saw here, is more normal-ish, even though it's got a strongly electron withdrawing character. So that puts it in the 2 and the 5 range. Okay, enough of this. So Ka and Kb, for the conjugate pair, right? HA makes H plus with A minus and A minus with H2O makes HA, H minus, right? You can write those equilibria here, and you can see that if you multiply them together, Kw is equal to the product of Ka and Kb. So Kw is equal to Ka times Kb. Kb is just the backwards of Ka with the water equilibrium thrown in there, right? So if you add these reactions up, HA cancels, A minus cancels, and you've got H2O makes H plus OH minus, right? And that is how Ka times Kb equals Kw. So, to find Kb from Ka, all we do is we take Kw and divide by Ka. So it's like Ka, Kb is Kw. So take Kw, which for all practical purposes is 1.0 times 10 to the minus 14. That's the room temperature value, right? I mean, nobody typically is going to do anything at 85 degrees, or it's even really close at 0 degrees, or I mean, say 4 degrees C. But so you can look up Kw, but for our purposes, let's use 1.0 times 10 to the minus 14, right? Ka is that. So this means this is Kb. So, and that's for acetic acid, right? So let's see. Let's see how that looks on the document camera, right? So we've got Ka times Kb equals Kw. This is Ka is H plus times A minus, right? And HA here is equal to H O2C CH3. Right? This is acetic acid kind of spelled backwards. So we've got H plus times O OCH3 minus. And there's a billion different ways to spell this. I'm sorry. I'm just trying to make it look like an acid here, right? And then this is over HA, which is H, O2C, CH3, times KB. And so Ka is equal to this, and then Kb is equal to reaction of acetate with water. So that's O2CH3 minus plus H2O makes HO2CH3 plus OH minus, right? And so the Kb here is going to be the product of these ions, right? So it's going to be OH minus times HO2CH3 divided by this guy here, which is O2CH3 minus. This is Ka, this is Kb, and this is going to equal Kw, right? Because this species here cancels with this one. They're the same. This guy here cancels with this one because they're the same. And all we have left is Kw, which is H plus times OH minus. This is Kw. Right. Anyway, so that's the kind of makes a little bit of a longer story out of it, but anyhow. So let's see here. So let's do chloroacetic acid here. Chloroacetic acid is this is probably monochloroacetic acid. Yeah, it's monochloro because I can tell there's monochloro, dichloro, and trichloroacetic acid, right? And each time you add the chlorine, you replace a hydrogen for a chlorine, this acidity increases, right? So this number becomes smaller. Or no, it becomes larger rather. It becomes larger. Sorry. The exponent here becomes smaller, negative value, right? So I'm just going to write down this Ka equals 1.36 times 10 to the minus 3 for chloroacetic acid. Okay, now let's find Kb here. So this is Cl H2C, right? CO2 H makes H plus Cl H2C CO2 minus. So the Kb will equal what here? Well, the Kb is going to be this ion here, Cl H2C CO2 minus plus water makes Cl H2C CO2H. Oops, extra C there. Oh wait, no, there's not an extra C there. There's just CC. So hold on. Cl H2C CO2H plus OH minus. This breaks down the water and makes an OH minus. It pulls a proton off the water, leaves an OH minus, right? So this guy here, this is governed by Ka, and this is governed by Kb. And we know that if we multiply these together, we get Kw, which is H plus times OH minus makes H2O. Oop, sorry, H2O makes H plus OH minus. And Kw is equal to the product of these ions, right? So Ka times Kb equals Kw. So if we're looking for Kb, that's equal to Kw over Ka. It's equal to 1.0 times 10 to the minus 14th over 1.36 times 10 to the minus 3, which will equal 7.4 times 10 to the minus 14 minus 3 is 11, right? This is Kb. And if I have any real-time fact checkers, you can work on me. I think I got that one right. So anyhow, that's how to do this. And okay, good. Here's another really good one. This is let's calculate Kb for methylamine. Right? Yes, Alvin.
Dr. Terry, I think that should be -10 because 1 over 1.36 will be 0.74.
Damn it! Damn it! Got me again. Curses! Curses! Alvin!
Yes, sir.
Wait, no, wait. Alvin! Okay, hold on. You're right. I messed it up. Damn it. Okay, so let's do methyl ammonium. Ignore my math here. So dead. Okay, so Kb for methylamine. I'm just going to write this down. Kb for methylamine, which is CH3NH2. That is equal to 4.47 times 10 to the minus 4. Okay, and find Ka. It's what, right? So here we go. So now in Chem 55, there's acids, which are strong acids like HNO3, HCl, blah, blah, blah. We don't normally treat their equilibria at all. And then there's weak acids. They're almost all carboxylic acids. Or, CO2, something, CO2H, right? And then there's bases. And bases are almost always like KOH, the strong ones. We don't care about the equilibrium for them. And amines. This is an amine. Because it's got a nitrogen and it's got an organic part here, right? So, that's just like something to keep in mind, because in exams, stuff like that, it's not that uncommon to say, say methylamine is mixed with water. What's the pH, right? And you're like, I don't know the reaction, whatever. But it's just a base reaction, right? So let's write out this reaction here. So this is CH3NH2 plus, it's a B, so we can add H2O, and that's going to make CH3NH3 plus OH minus. And the Kb will equal CH3NH3 plus concentration times OH minus concentration divided by CH3NH2 concentration. So here's an interesting little factoid that this amines, they all smell like fish. They're all kind of nasty, and some of them are really nasty, right? And so if you have an amine solution and you want to kill the smell, you must favor this form. This is not smelly, but this stinky, right? So the not smelly form is favored by the addition of acid to this guy. And we'll look at that in a second, right? We'll look at the Ka, right? So the Ka is, we're gonna take this product, right? It's this guy here, CH3 NH3 plus makes H plus the stinky part, CH3NH2. So this is the Ka, right? Because it's making acid, right? So and Ka is equal to numerically H plus times CH3NH2 over CH3NH3 plus. Okay, so the question is, what's Ka? What's Ka here, right? So Ka is this times Kb, right? And you'll notice here that Ka times Kb is equal to, I'm just going to write it out this once, right? Is equal to H plus CH3NH2 over CH3NH3 plus times Kb, which is CH3NH3 plus times OH minus over CH3NH2, which is just equal to Kw, right? Because this guy cancels with this guy cancels with this guy, right? So Ka times Kb equals Kw equals, so therefore, we're looking for Ka is equal to Kw over Kb is equal to 1.0 times 10 to the minus 14th over 4.47 times 10 to the minus 4. And this is 2.224, 2.2 times 10 to the minus 11. The pKa is the base 10 log of that. It's a negative base 10 log of that. So the oops. Oh, the pKa is equal to minus 10.06 because the pKa is negative log of Ka. Oops, sorry, I'm off screen. It's 2.2. Decky. show. So this is basic. This is the pretty easy water equilibria stuff, right? There's no, it's all still just straight algebra with no substitutions, right? And substitutions will come in later chapters. I think probably we'll
Dr. Terrell,
yes.
did you find that PK just doing negative log K, negative log 2.2 times 10 to the power negative 11?
Yes. Yes.
I got 10.65. That's why I was wondering.
Oh, you're right. You're right. Damn it.
Okay.
Damn it, Alvin. Damn it.
Sorry.
Plus 10.65. Is that
Yes,
minus?
plus.
It's plus
Plus.
10.65.
Yeah.
It's two mistakes. Ah. Oh my God, Alvin, don't tell on me, please. Oh, Omar said it smelled fishy. It did smell fishy. Oh, God. Oh, no. Oh, geez. I suck at this. Okay, next topic, please. Hold on. Oh. There we go. So, this is all they give you, right? So, so we can, let's not even do this one. So, so here's, okay, so there's some notation, right? This I'm not going to belabor, right? It's just that for a monoprotic acid, KAB, Ka, Kb equals Kw. For a diprotic acid, it's Ka1 times Kb2, right? It's just about the number they put here, right? And this is B2 because this is the second base reaction of A2 minus. It doesn't really matter, right, what these numbers are. You just have to find the proper one that cancels, right? Ka1, Kb2 is Kw. And then Ka2, Kb1, right, is Kw. That's another one, right? And so don't worry about the numbers here too much. If it doesn't make sense to you, just make sure that when you multiply the Ks, all these species except H plus and OH minus cancel, right? So anyway, and Kw is H2O makes those guys, right? Then for a triprotic, it's 1, 3, 2, 2, and 3, 1. So don't worry about that too much. Now, for some reason, Harris likes to take a little segue here and talk just a teensy bit about stereochemistry and the way that you write organic molecules, right? And I know 99.9% of you have had organic chemistry, and this is a total review, but it really can't hurt. So here goes, right? This is epinephrine or adrenaline, right? Or epinephrine, right? And this is a full drawing of it with all the important stereochemistry, right? The stereochemical center here, there can be more than one, but in this case, just this carbon, right? Has one hydrogen going into the plane, one hydroxyl coming out, right? You know this is stereochemically active because this carbon has 4 different groups on it. So there is two isomers, a D and an L or an R and an S isomer, right? R and S you get from the naming conventions. D and L you get from experiment, whether it's dextro or levo rotatory of polarized light. That's not important. What's important is that the dashed line means it goes in, the bold line means it comes out of the plane, right? Now, another way to write this is like this, where you have hydrogens implied at every carbon-carbon bond. Then this one is stereochemical, so they explicitly include the hydrogens. Then there's another CH2 here, which we just friggin' ignore because it's you can shorthand it like this and everybody knows. And then it's NH2 and CH3, right? And the CH3, you could just draw a line there and have a line end, right? But a lot of times you'll include the CH3. Anyway, that's just that. And then the other thing is that benzene is a resonance structure of smiley face and upside down. No, frowny face, whatever, and this guy. And so it's normally drawn with a circle, right? So don't get caught in there. All right. So this is chapter 6. What I wanted to do is look at some of the homework in chapter 6. So yeah, I know it's kind of crazy, but anyway. So what happens is sometimes these questions come up, like in his class, and then he states it, and then he puts it in the friggin' book, because it's like for some students that'll come up. Okay, so what I wanted to do is I wanted to go over the homework, right? And there is the homework, right? 6A here. And we're starting on 6B, right? So I'm going to do a couple of homework problems from 6B to kind of get you going on it. Because I was flummoxed the first time I got to this, like, what the hell's going on here? And it turns out it wasn't as bad as I was thinking. But so let's take a look at some of these homework problems. 6A and 6B. I'm basically doing your homework here, but that's okay. So, let's start with this guy here. Oops, I'm authorized. Oh, I gotta friggin' log back in. Log in. Log in, man. You've got to log in. Okay. So here's our problem, right? And it has the numerical answer, right? Which I kept getting wrong, of course. And so what I'm going to do is I'm going to go ahead and go over that with you. And it's going to be a little bit tedious, but I'll handle the tedious. We've got calcium phosphate hydroxide, right? It's kind of a weird sort of a complex ion, but this hydroxyapatite is what your teeth enamel is made of. Yeah, I know. It was a little bit hard to solve, wasn't it? So let me just do it, right? And then we can work through it. So calcium, hydroxyapatite makes calcium, phosphate, and hydroxide. And the KSP of this is a monstrous 2.34 times 10 to the minus 59, right? So that means that your teeth aren't dissolving super quickly, right? But if you have OH minus fixed at 2 times 10 to the minus 6, right? That means that your the pH in your mouth is like 6.8, right? No, 5.8. 5.8. 2, 6, 9. Yeah, 5.7. pH is 5.7, right? It's not that uncommon, right? What is a calcium ion concentration in this solution, right? If nothing else changes. And so let's see how that works, right? So we've got calcium. Calcite or aragonite, right? No, wait, hydroxyapatite, sorry. And this is a solid, right? And this makes 10 calciums plus 6 phosphates plus 2 hydroxides. And KSP here is equal to just the product of these ions raised to their coefficient. So it's calcium raised to the 10th power phosphate raised to the 6th power hydroxyl squared is equal to 2.34 times 10 to the minus 59. Holy cow. So the what they specify here is that OH minus, OH minus is equal to 1.20 times 10 to the minus 6, right? And they're saying find calcium 2, right? So I worried about this a lot. The first time I tried it, I did it right, but I got the wrong answer and I freaked because I thought we were supposed to calculate phosphate from some water equilibrium. And I thought, oh my God, what's going on here? Yeah, so don't worry. I'll give you plenty of time to do these guys. Don't worry. And they're not all this hard, trust me. But anyway, I'll go. And I haven't assigned 16, right? Because I'm going to be slashing some of the problems, right? Not necessarily the ones I do here, just some of them. Right? So we're just going to assume this guy's fixed, right? By some other equilibrium in solution, right? That means that calcium and phosphate are they're linked stoichiometrically because we make 10 and 6, right? So if calcium, if we let it be X, then phosphate will equal what? Well, phosphate is going to be equal to 6 over 10 times X, right? 0.6X, right? So, so what we can do is we can go ahead and solve this. We can say that X to the 10th times 0.6X to the 6th times 1.2 times 10 to the minus 6 is equal to 2.34 times 10 to the minus 59, right? So the way we do this is we're going to separate this into terms. We got X times X to the 6th. That's X to the 16th times 0.6 to the 6th times 1.2 times 10 to the minus 6 equals 2.34 times 10 to the minus 59. We can sort of 0.6 to the 6th is 0.04666. Right, and then we can collect terms and say X to the 16th is equal to 2.34 times 10 to the minus 59 divided by 1.2 times 10 to the minus 6 times 0.04666, right? Which equals 3.4826 times 10 to the minus 38. And I'll tell you why phosphate is 6/10 of x. So then x will be the 16th root. 3.4826 times 10 to the minus 38, right? And so you got to be able to get the 16th root of stuff, you know? And this is very large, this is very large, but they sort of cancel out. And this comes out to 0.001442. Right? So it's, and so to put this in proper sig figs, right? So this is calcium. We're going to round it to, there's 3 sig figs, there's 3 sig figs. So we'll round this to 3 sig figs. So this is going to equal 1.44 times 10 to the minus 3. And that is actually, I think that's the correct answer here.
Yes, that's what I got too. But Dr. Terrell,
Yeah.
Just the calculation above that, is that is that 2.34 times 10 to the power negative 59 over 1.2 times 10 to the power negative 6 times 0.04666?
Yeah.
So when I did that, I got 4.18 times 10 to the power negative 52. But your answer for the calcium is, that's what I got at the end. I got 1.41 times 10 to the power negative 3, but it's that.
Wait. Sorry. The point of, wait. It's 1.2. This guy is squared.
There you go. Okay then.
Yeah, that's squared. Sorry about that. Yeah, I'm going off notes I made, and obviously I'm screwing it up. I'm sorry, but there's it's a KSP. That times that. So this is 6. That's squared. Right. So OH minus is this. So the OH minus is this guy squared. Oh gosh, I completely omitted that. Yeah, sorry about that. That sucks. And thank you so much, Alvin. You're saving my butt.
Yeah, and Dr. Terry.
Yeah.
So, and
not again.
3.48 is fine. 3.48 is fine times 10 to the power 46.
Oh, 46. Thank you.
Yes.
That makes sense. Oh, 46. Oh, yeah.
And 0.00144. Cool. Yeah, there you go.
Okay. Thank God. I omitted just a bit. Oh, God. Okay. So, Omar asks, why is phosphate 6/10 of x, right? This is because that's how they're born, right? You know, when this guy dissolves, you know, it's making calcium and phosphate at a fixed ratio. Every 10 calciums makes 6 phosphates, right? So there's a 10 and a 6 there. So if we let this guy be 1, then this is going to be 0.6. So say divide them both by 10, right? Then phosphate will be 6/10 of x, 0.6x.
Yeah, the solubility.
Yeah.
And also it can be done with the ice table, correct, Dr. Terrell?
See, yeah. That's a bit. Oh God. Oh no. I'm sorry. The ice table.
Yes.
What's the ice table?
Oh, initial change and equilibrium. If you just let that calcium 2 plus be 10 as initially it will be 0. change would be 10s. S will just be the solubility. And if you do that, equilibrium will be 10s2, right? Wait,
sounds
did you
right.
just say what is ice table?
Yes. What is the ice table? I've never heard of it. We haven't learned ice.
For solubility, we always did ice table, and we are still doing it in our, like physical chemistry too. It's just, what is the initial concentration? What was the change? And what is the equilibrium in the equilibrium chapter?
All right.
Yeah.
It makes sense. It makes sense. I kind of get that. It's for organizing stuff, right? Like Elizabeth says there. So I don't know. I don't want to belabor it, but that makes perfect sense, right?
The formula would be same, the one that you have written. KSP equals C,
right.
concentration of Ca, PO4, OH minus 2. But the value would be, Ca would be 10s power 10, PO would be 6s power 6, OH would be 1.40 times 10 to the power negative 6 plus 2x. 1.2 times 10 to the power negative.
Right. Well, yeah, actually, but it would be plus 2x, right?
Yes, plus 2s, because
but they said it's fixed. In this case, it's fixed. So it doesn't get to be augmented by the dissolution, right? It's controlled by a buffer.
Okay.
All right. I'm just I have to be right about something here.
Yes, muchas gracias.
Muchas gracias a usted. Oh my God. I'm going to do a different one. I'm thoroughly humiliated here. Okay, so let's see here. Next problem. Oh, geez, I have 0 time. Okay, next problem next time. So will we give in full chemical reaction during the test? 95% of the time. It might be the case, Omar, occasionally, that you'll have to say, what is the Ka for methyl ammonium? Right? It's possible, it's fair game to say that, right? Now that's an advanced problem because it's mixing together Ka and nomenclature, and it's asking you to have a more comprehensive understanding of stuff, right? So I'm not going to do it a lot, maybe just a little bit, okay? Thank you for asking that question. That's a good question. Damn it, I didn't even get through my notes. If it weren't for Alvin, we'd be on the wrong track, and I'd be spewing misinformation, like a certain politician I know. Yes.
Are you indirectly telling me that I made your time? No, I'm just kidding. I was like, it's because of you, Alvin.
You have to be brave, Alvin. You have to be brave. Don't be afraid of me, for God's sake.
Yeah,
yeah, exactly.
That afraid is not that kind of afraid. This is just kind of like it's a expected afraid, you know?
Yeah, don't worry.
Yeah.
I love all you guys. Just don't worry about it. I need help, man. I need help. It's weird teaching I make a lot of mistakes, and I'm sorry about that. I suck as a Chem 55 professor. I know it, right? But it just really helps me to have somebody fact check me like this. So, even though it does slow me down a little bit. So, okay. All right. So I'm so sorry. I got to go now because I can't hold you guys so much longer. But I do have office hours at noon, so please log in for that if you want. Okay.
Thank you, Dr. Terrell. Have a good one.
Thank you, everybody. Thank you. Bye-bye.